So you're welcome back to the channel, and in this place, in the continuation of our Laplace transform series, we are here to prove the Laplace transform of sine kt is equals to k over s square plus k square. So now let's move on with our videos. So now we put it into our basic form. We have our f of s, or let me just put it in this form. We have the Laplace transform of sine kt to be equals to the integral from infinity to 0 of sine kt e raised power minus st. We have our dt. So the Laplace of sine kt is equals to this, right? So now moving on, we use integration by parts, and integration by parts, as I mentioned earlier, we have our integration of u dv would be equals to uv minus the integral of v du. And if this has any bounds, like from b to a, that means we are going to be applying b to a here and b to a here also. So we move on. I make my sine k equals to u is equals to sine kt, and we have our dv is equals to e raised power minus st. So therefore I have my du is equals to, now if we differentiate this, we know that it will give us k cos kt dt. So I did not have time to be going through this because we are going to be having a long time ahead of us. And this I did it through chain rule. I used chain rule. Make this use sub to do this, and then we have dy dx is equals to dy du times du dx. That is what I did. As easy as that. Then we move on, integrate this. We have our v is equals to e raised power minus st over minus s. So therefore, using our integration formula there, we are going to be having our Laplace of sine kt is equal to, now u times v is equal to, we have sine kt times e raised power minus st over minus s. That is u times v. Then that one will now be from infinity to 0 minus the integral here from infinity to 0 of v du. So we have our v as v du is equals to k cos kt times e raised power minus st dt. We have this over minus s. Here e raised power minus s. If we multiply it v du, this is what we are going to get out here. So now let's focus on the left part first. If I put my infinity and 0, I'm going to be having it as this one here. I'm going to be having it as sine infinity over, no, you should not forget that e is raised power minus, so that means it's coming down. E raised power infinity sorry, we have our minus s times e raised power infinity. Then on the other hand, we have minus, put our 0 here, we have sine 0 over e raised power 0 minus s times e raised power 0. And on this edge, this is going to be giving us sine infinity is equals to infinity divided by e raised power infinity. That is when it will give us 0. Anything divided by infinity is equals to 0. So therefore, we are going to be having 0 minus sine 0 is equals to 0. So we already have this as 0. So therefore, we have this entire place to give us 0. Now to this other side, we can bring out the constant k and minus s. So the minus here will cancel the minus here. So therefore, we have it plus k over s. We are bringing it out. Then I have our integration from infinity to 0 of cos kt times e raised power minus st. So now we know that this is equal to 0, right? So That means we know that Laplace of sine kt here, so we have Laplace of sine kt will be equals to, we have our 0 out of it, then we have k over s times the integration of cos kt times a raised power minus st. What does it look like to you? It means that this is the Laplace transform of cos, that is the Laplace transform of cos kt. Now this is what it seems like. Let's not forget our dt over here, our Laplace transform of cos kt. So now let's move on. So if we move on with this, like we know that this is equal to the pattern of cos kt, but we cannot just make an assumption the same way that we made an assumption about t raised power n. Here we are going to continue integrating because we are trying to do some type of factorization over here. So now this over here, I'm bringing it here, which is our we have our Laplace transform of sine kt is equals to k over s. The Laplace transform of cos kt is this form right here, which we know. So this will be integral from infinity to 0 of cos kt times e raised power minus st dt. We make our u to be equals to cos kt, and we have our dv to be equals to e raised power minus st. That means our du is equals to, if we differentiate this, we have minus k times sine kt dt. And here we would have dv here on this side, that is, so here we have v will be equals to e raised power minus st over minus s. So now that we have gotten that, we can just put it into a formula. First of all, I bring my k, we have it as equals to k over s into my big bracket first of all, and now I impute my values, u times v here. We have cos kt times e raised power minus st over minus s, yeah, over minus s. Then we have that this will be from infinity to 0, we have minus the integral from infinity to 0 of v du, which will be equals to, we have minus k sine kt e raised power minus st dt over minus s. Now let's just simplify this. We know that our bracket, so we close our bracket over there. Let's simplify this. We get this as equals to k over s in the big bracket over there will be equals to, now this over here, what is this going to give us? Let's take a little bit of time. If we put infinity here, we are going to be having cos infinity over minus s times e raised power infinity, that is on this one here, minus cos 0 over minus s times e raised power 0. So let's move on now. Let's still move on for now. Now we bring out this constant minus k and minus s. Here we have minus cancel minus. So we have our minus which is outside there. Then we put our k and s outside. And then we are going to be having the integral from infinity to 0 of sine kt times e raised power minus st dt. So now we know cos infinity divided by minus s times e raised power infinity divided by infinity, everything divided by infinity is equal to 0. So we know that this here is 0, and on this other side cos 0 is equals to 1. and e raised power 0 is also equals to 1. So here we'll be having equals to k over s of the big bracket. Now on this bracket here alone, we are going to be having 0 minus, we have 1 over minus s. So in this particular case, minus cancel minus, we can just assume, and we just simplify it, and we have 1 over s over here. That means this entire thing gives us 1 over s. And here we have minus k over s. But what does this look like to you? It looks like the Laplace transform of sine kt. Now, we know that from here, let me take out this borderline. This is what we did. This is what we did that got us here. So we know that um, the Laplace transform of sine kt is what is giving us this. So therefore, I will have to simplify this a little bit. I will have my Laplace transform of sine kt on this other side. Now expand the bracket. We have this as k over s squared minus k squared over s squared Laplace transform of sine kt. Now we are not done. So from here, we should be able to see it now that we are going to just simplify, we are going to collect like terms, and then we are going to be doing what we call, we are going to be making our Laplace of sine t the subject of the formula. That is what we are going to be doing. So let me make some space over here. Let me make some space over here. I'm going to be having our Laplace transform. Now, look at this Laplace transform of sine kt. Everyone that has Laplace transform of sine kt, we are bringing it to one side, and every other thing we are bringing it to the other side. So you have Laplace transform of sine kt on this side, then this one here we are bringing it to the other side. We have plus, like this minus will become plus k square over s square Laplace transform of sine kt is equals to, we have this k over s square. So now from there it should be easy for us. We just make Laplace transform of sine kt the subject of the formula. We have our Laplace transform of sine kt into bracket 1 plus k square over s square is equals to k over s. So we first simplify inside the bracket. We have the Laplace transform of sine kt into big brackets. If we simplify this, we are going to be having that s, then we have here s squared plus k squared is equal to k over s. So what we just do is divide both sides by this over here. That is, if we divide both sides by s square plus k square over here, we have our s square, and we do the same thing for here, s square plus k square over s square. We are going to be getting our answer. So let me just do it over here. If I divide both sides, I will have my Laplace transform of sine kt to be equals to k over s divided by s square plus k square over s square. And this here is going to eventually give us Laplace transform of sine kt is going to give us k, that is the s square here. Let's not forget the s square here. Okay. The s square here divided by the s square here, bring it, we are going to be having s over k over s square plus k square. Right. This is going to be giving us this over here. So thank you very much.